the ratio of the absolute value. So suppose that, okay. Now this ratio, if you have a unique largest eigenvalue, that ratio is going to be less than 1 in absolute value. But let's suppose it's near 1. The power method will still converge, but very, very slowly. So it's quite ineffective. So power method is not really a very reliable algorithm, unfortunately. Interestingly, though, Google has other choices for finding the largest eigenvector predict once, but it finds that the power method really works best for what they need. And they just need this one eigenvector. We don't need all of them. But a lot of it depends on how the eigenvalues of the matrix behave. If you have a matrix that has certain properties, like you know that there's a dominant largest eigenvalue, then yeah, power method is a really good bet. Okay, but we need some way to get around these drawbacks. So here's one workaround. It's just a variation of a power method, and it's called orthogonal iteration. And you'll see in this form, it's very similar to the power method. So instead of choosing a single vector, I'm choosing a matrix that has R columns. And I want the matrix to have R orthonormal columns. So it satisfies this relationship here. So then what I do is okay, so I take my QK, multiply it by A like in the power method, and I'll call that ZK. And then what I do is, in the power method, I just took my result and normalized it. I made it a unit vector. I'll do the same thing here, except I still want them to be orthonormal. So what I do is perform a QR factorization. So that's what's going on here. And you can use the tools that I described before, like household reflections or Gibbons rotations, to compute that QR factorization. And you keep going, again, until you get convergence. So this will get around the problem of, for instance, if you have two jointly dominant eigenvalues. So what this does is orthogonal iteration computes the largest R eigenvalues. But the convergence rate is determined by the ratio of lambda R plus 1 over lambda R. Now, that ratio could still be close to 1, and you can still get poor convergence or maybe no convergence. So it's really just pushing a problem down the spectrum. But at least we can still use this in order to try to compute more eigenvalues more efficiently and build a method eventually for computing all the eigenvalues. All right. Now, so in fact, what I can show is, dang it. Okay. Need to be careful with my notation going forward because I did my indexing a little differently than I did in notes. Okay, actually, the main difference is how I indexed the Q's. Okay. All right. I can work with this, I just have to be careful. All right. So one interesting property of orthogonal iteration define the matrix RK that actually comes from QR factorization. So that is equal to QK plus 1 Hermitian transpose ZK. But the way I define ZK in the algorithm is AQK. So what that means is if these QKs converge to Q, then what happens is these matrices, I have different matrices on either side of A, but if the Q's converge, they end up being equal. Then I have QHAQ is equal to R, which is an upper triangular matrix because it's a QR factorization. And that means what I have is Q is equal to QR. And what it means is the columns of Q span an invariant subspace. And what that means is your R columns of Q, the little r in this case, they're not eigenvectors. However, they are linear combinations of the eigenvectors from the first R eigenvalues, the largest ones. So what you can do is you can try to solve a much smaller eigenvalue problem in order to figure out what the eigenvectors actually are. The first column of Q will be an eigenvector for the largest eigenvalue at least. Okay. But the case that's actually the most interesting is I can let little r, the number of columns in my Qs, I can choose that to be anything. But let's let little r equal to n. So I just apply orthogonal iteration again. So for instance, I can choose Q naught to be the n by n identity matrix. And I can just keep multiplying by A and QR factorizing. So what happens is we obtain, if the iteration converges, which it usually will, not always, what I get is QHAQ is equal to some upper triangular matrix T, and this is the Schur decomposition of A. But unfortunately, this convergence is generally quite slow because if you have any two eigenvalues that are clustered closely together, that's going to slow down convergence. But the thing is, it's still this starting point for building a more efficient algorithm. But what we're going to do is, we're actually not going to use orthogonal iteration as I've originally described it. We're going to fashion it into something that is easier to work with. Okay. So I'm going to define a matrix TK that is equal to QK Hermitian transpose A QK. Now, because my notation is slightly different from notes, I got to set aside the notes, so hopefully this will still go correctly, but I believe it will. TK is not upper triangular. However, if orthogonal iteration converges, it will converge to an upper triangular matrix eventually. So what I can do is keep in mind that AQK, if we look at back to the previous board, the algorithm, that is equal to ZK, but ZK has a QR factorization, that is QK plus 1 RK. Now, QK plus 1 are both orthogonal or unitary matrices. So, therefore, their product is also unitary. So, I'm going to group these together. So this is unitary, so the complex analog of orthogonal, and this is upper triangular. So what we have here is a QR factorization of this matrix here, TK. QR factorization is unique. So that's one important thing to point out here. Doesn't matter how we get it, but okay. Now, let's take a look at the next matrix in the sequence, TK plus 1. Now, by the definition that I used up here, that's QK plus 1, Hermitian transpose A, QK plus 1. All right. Now, okay. I have to be careful with my manipulations here to get this right, but at least I know what it is I want to get. Okay. So I have. Okay, got it. I'm going to insert in the middle here QK Hermitian transpose, because this is a unitary matrix, so this is identity. And then I still have QK plus 1. And then I'm going to group these together. Okay. Now, AQK is ZK. So QK plus 1, Hermitian transpose ZK, QK, Hermitian transpose QK plus 1. But QK plus 1, Hermitian transpose ZK, I have that up here. That's RK. So I have RK QK plus 1, Hermitian transpose Q. Oh, that's not right. QK, Hermitian transpose QK plus 1. I'll group those together. Okay, so let's take a look at these expressions. TK is equal to this QR factorization. The next matrix in the sequence that's converging to something upper triangular, TK plus 1, is equal to that. If you look at what I've boxed, what's the difference?
They're, well, RK's multiplied on the left, the right.
Yeah, as Floyd's head gesture showed. Yes. Here we have a QR factorization. The next matrix, we've multiplied the QR factors in the opposite order. So now the thing is, suppose I let, for simplicity, I'll let Q0 be equal to identity. Then T0 is Q0HAQ0. That's just A. So here's what I can do. I can start with just A, QR factorize it, using whatever approach I want. Household reflections, Gibbs rotations, whatever. Even Graham-Schmidt, but it was a terrible idea.